Hello, everybody. Today we're going to talk about proofs. And theory classes are usually pretty fond of proofs, and there is a reason. We're not insisting on proofs because uh, proofs are important for the sake of themselves or because of some formality bar. We're insisting on it because proofs are important, and you don't really understand things until you prove them. And each one of us, I definitely have convinced myself of wrong things, and until I actually sat and tried to prove them, I couldn't see the bug. But proofs are also one of the challenges of this class. And the challenge is to come up with the right level of proof for any given point. And this requires some mathematical maturity. I see a typo here. And that's something that theory classes and math classes give you. And over time, all of you will feel more comfortable with it. What I'm going to do here is to try to give you a few hints about how to approach proofs. And hopefully this will help you. And if not, then I and the TAs are here to help you. So, what makes a mathematical proof a good proof? So one thing, it should be clear. It should be easy to understand what you're writing. You cannot prove things just by obscuring them to the point that people do not understand. If you cannot understand, then you didn't prove it. Then you want proofs to be correct and convincing. And convincing means different things in different scenarios. So if you write a paper, the reviewer should be convinced that what's there is correct. And in a class like this, what we should be convinced is not only that what you're saying is correct, but that you actually understand it. So that there is an entire proof behind it. If we force you to write a complete proof, you'll be able to do that. So that's the level that we are expecting. A level that perhaps doesn't contain all the details, but makes it extremely clear that you know all the details that need to be proven. And finally, a good proof is like an augur or a parfait. And if you don't know this reference, please click on a link in my homepage that is as important for your cultural development as anything else in this class. But specifically what I mean here is that a good proof has layers. And kind of one way of thinking about it is that the core of the proof, all the technical details, are really what makes the proof go. This is the most important part. Without the technical details, there is nothing there. You cannot philosophize about it and say, okay, it's proven. So you need the technical details. They give the warmth to the proof. They give the content to the proof, but they're also kind of too hot to touch. You can't handle them directly. It's very hard to read just the mathematical equations and derivations and all of that. So what we do is that we cover this this hot part with various levels of intuition in different parts of the proof. And this allows us to understand what's there. And then by the time we get to the actual technical levels, we understand enough so we can handle them. So that's how I like to think about a proof. So you'll be judged by whether the proof is convincing, correct, clear, and to make it all of this run, you need to give us all the layers. You give us enough technical details, but also enough intuition to cover it. And Sipser in his book gives a particular formula for that. I don't necessarily follow exactly that formula, but Sipser does know a thing or two about writing. I think the book is very well written. And perhaps having a formula is good when you're just starting. So the formula talks about 3 levels of detail. The first is kind of a short phrase or sentence or hint about the proof. And I would say it can become a paragraph rather than a sentence. Say that it's proof by contradiction, proof by induction, follows from the pigeonhole principle. Then you have a short description of the main ideas, and perhaps a paragraph, perhaps a little bit more. And finally, you give the full proof. And I would say, emphasize that even within the full proof, it's good to go back to the intuition and remind us, okay, this is where we do what we discussed previously. So this corresponds to that intuition. So this is a good formula to follow, especially when you're starting to deal with proofs. What will we do in class or in these videos? In these videos, we will not have all the technical details. It won't be a complete proof. We won't deal with this third level of the proof a la Sipser. And the reason is that videos and presentations, and when you'll give research talks in the future, hopefully, these are not the place to give all the technical details. If I'll do that, you'll hate me, I'll hate myself, and you'll get very, very few, very little value out of it. So what would be valuable is to think about the proofs as I give them in these videos and in the lectures that we'll have, and try in your mind to fill in the details. And that will kind of tell you if you can, if you really understand it. This is not a requirement, but it can be useful for you. So if you can fill in the details, it means that you really understand it. So some methods of proof. This is not something I'm going to teach you. You should have learned a lot of it in CS 103 or in other classes. And I would recommend you to look at Sipser at his first section that gives a lot of kind of the details that are kind of preliminaries to this class. But basic methods of proof that you probably are aware of are constructions, contradiction, induction, and strong induction. And the one that is really useful for this class, so I coin it best friend for this class, is reductions. And we'll see a lot of reductions, and this is really extremely useful later in your research life, scientific life. Reductions let you connect one problem to the other. So here is a joke that usually is given at the expense of mathematicians, but mathematicians like me are very proud of it. So we very happily share the story ourselves. And this is a story about reductions. So you have a mathematician and they need to fill the bucket. And I think one version of this story is that they fill the bucket for because there is a fire, but while this is recording, California is burning in a lot of wildfires. So let me revise it to say that they need to fill up the bucket to clean the house. So there's a problem. The bucket has a hole in it. But the mathematician is smart, so she plugs the hole, fills the water, and then able to plug the bucket and then fill the bucket with water, and then can clean the house. And everything is great. The next day, the mathematician still needs to clean the house, but now she has a bucket that doesn't have a hole, and she thinks, okay, how would I solve it? What would I do? And she said, okay, yes, I'll make a hole in the bucket, and then by reduction, the problem is solved, because from there I know how to handle it. So she makes a hole and then go rest. And as I said, this is at our expense, but we're actually very fond of it. At least I am very fond of it. So let me give you one example of one proof, and let's try to do it with a little bit more details and then I may for such a problem, just to remind you kind of what proofs look like. So suppose you have a set, which is a subset of the integers 1 to 2n, and the size of the set is n plus 1. Show that there are always two numbers in A, such that one number divides the other number. And I suggest that you stop the video now and try to think about it for a few minutes. I don't think it's that easy to prove it. Here's an example. If you have a set A, which is subset of 1 to 4, you see that 1 divides every number. So every set that contains 1 would satisfy this property. And if A isn't there, then A has to be 2, 3, 4, because it has to be of size 3, and then 2 will divide 4. Yes, checking special cases, simple cases is a good idea. So, but we still want to prove the entire problem. Let's look at two hints. The first hint is the pigeonhole principle. If 6 pigeons occupy 5 holes, then at least one hole will have more than one pigeon. 6 pigeons, 5 holes, and then 2 holes have to have 1 pigeon. And this can be generalized to any n plus 1 pigeons that occupy n holes. And then there will be 1 hole with at least 2 pigeons. If there are more pigeons than holes, then there has to be a hole that contains 2 pigeons. Another hint is that any integer, a, can be written as 2 to the k, some power of 2, times m, where m is the odd number, an odd number. It can be proven by induction if m is not odd, you can divide it by 2, and then you'll get 2 to the k plus 1 times m prime. And so eventually you'll get 2 to the k times an odd number. We'll call m the odd part of A. Okay, so now given these two hints, if you want, you can again freeze it and pause it and then try to solve it yourself. So here is the proof idea. Given the set A, you're going to use the pigeonhole principle to show that there are elements A1 and A2 such that both of them have the same odd part. So A1 is 2 to the I times M, and A2 is 2 to the K times M for some odd M. And in that case, one will divide the other. So now let's get to the as much gory details as we're willing to give in this class, and the proof will be by induction. So each number element of A can be written as 2 to the k times m, where m is odd. And the odd number is going to be, because A is between 1 to 2n, the odd number is also going to be in 1 to 2n. But observe that there are n odd numbers between 1 to 2n. And there are n plus 1 numbers in A. Therefore, by the pigeonhole principle, there are two elements with the same odd part. And let A1 and A2 be such. A1 is 2 to the I times M, A2 is 2 to the K times M. One must divide the other. Thank you, thank you. That wasn't very difficult. Eventually in our class we'll have things that are more impressive, but I appreciate your enthusiasm.